So this is the values that we're going to plug in for x. X equals to -2 all the way to +3. So we do ourselves a little table. There's x. The f of x is the same thing as y. So so let's plug in the values for x. So when x is -2, right, we're going to plug in -2 for the x's. This should give us +1/4. So when x is -2, y is 1/4. Now let's use when x equals to -1, right? We plug in -1 for the x's. That's going to give us 1/2 to the first power, which will give us 1/2. So when x is -1, my y is 1/2. Now let's plug in 0 for x. So when x is 0, y equals 1. Anything to a 0 power will always be 1. Now when x equals 1, 2 to the first power will give us 2. So when x is 1, y is 2. When x is 2, y is 4. And finally, when x is 3, y is going to be 8. So there's my graph. You see? If you notice, right, when x is -2, the y will be about 1/4. When x is -1, my y will be about 1/2. When x is 0, my y is 1. When x is 1, my y is 2. When x is 2, my y is 4. When x is 3, my y is 8. Hey guys, this is the reason why we don't use, these are the numbers that we usually use, but right, because if we put 4 when x is 4, it's going to give us 16, and 16 will be way up here. It's going to be off the grid. That's the reason why these are the values that we plug in for x, like from -2 all the way to 3. It depends on your base. Okay. Now, if you graph f of x equals to 2 to the power of x minus 1, right, we do the same thing, right? Same values. Okay, now when it's -2, right? So we're going to plug in -2 where the x is. It's going to give us 2 to a -3. It's going to give us 1/8. When x is -1, right, it's going to be -1 minus 1 and give us 2 to a -2. It's going to give us 1/4. So when x is -1, my y is 1/4. When x is 0, right? When it's 0, we plug in 0 where the x is. So 0 minus 1 will give us 2 to a -1 power. It'll give us 1/2 to the first power, or 1/2. The answer will be 1/2. When it's 0, it's going to be 1/2. When x equals 1, it's going to be 1 minus 1 will give us 2 to the 0, which will give us 1. So when x is 1, my y is 1. When x is 2, we plug into 2 for the x is, so 2 to the power of 2 minus 1 will give us 2 to the first power, which results in x equals 2, y equals 2. When it's 3, it's going to be 2 to the 3 minus 1 and give us 2 to the second power will give us 4. And finally, when it's 4, 4 minus 1 is 3, 2 to the third power will give us 8. Hey guys, let me go back real quick. Hey guys, so this graph really, guys, it's going to be a horizontal shift because it's x minus, right? If it's minus, it's going to go to the right. So every point on the first graph on number 1, it shifts 1 unit to the right. So everything goes 1 unit to the right. That's where we got these values from. Okay. And again, I repeat, every value from number 1 moves 1 unit to the right. Okay. That's how we graph that graph. Now, number 3. Right, we have to rewrite it by using the rules, exponential rules. So 2 to a -x is equal to 1/2 to the x power. Right, so here, guys, instead of plugging values, right, so we're going to plug in the same values from -3 to 3. And we plug in -3 here, guys, right? It's going to be 1/2 to a -3rd power. So here, guys, we're going to make the exponent positive, and the base, we use a reciprocal. That's a rule. So it's going to be 8. Right? That's where the 8 comes from. And then we're going to repeat the process for the rest of the x values. Right? So when it's -2, right, we're going to plug in -2 here. It's going to be 1/2 to a -2 power. So you do the reciprocal, and the -2 becomes positive. So it's going to be 4. That's how we got all these values here. And the graph will be going this way. It's called exponential decline. Okay, because it's going down. And again, when it's -3, right? Here's my -3. It's going to be 8. When it's -2, it's going to be 4. When it's -1, it's going to be 2. When it's 0, it's going to be 1. When it's 1, it's going to be about 1/2. When it's 2, it's going to be about 1/4. When it's 3, it's going to be about 1/8. Okay, so the graph is an exponential decay or decline. Okay. Now this is number 4. It says the assets in billions of dollars for a Prudential Financial Incorporated can be approximated by the function AX equals to 315 e to the power of 0.056x, where x equals 7 corresponds to the year 2007. I guess here's the key. Is the key right here. It says that x equals 7 corresponds to the year 2007, which means, right, if the year is 2000 and x equals 7 corresponds to the year 2007, so then for the year 2000, x must equal to 0, right? X equals 0 corresponds to the year 2000, and x equals to 12 corresponds to the year 2012. So for a part, I'm going to evaluate the function at 0, a of 0, which means I'm going to plug in the 0 where the x is. It's going to give us 315, right? So it's going to give us 315 billion. The answer has to be 315 billion because the assets are in billions of dollars. Now, this is good to know. When t equals 0, right, this is your initial value. This will help you for the next problem in number 5. Okay? The initial value is when t or x equals 0, the value for y, this will be the initial value of the 315. Okay? Now for B, right, so we're going to evaluate it A at 12 because we're looking for the assets in the year 2012. Right, you plug in the calculator, and there's your result. 616.817155. Maybe you can round it off to your nearest tenth. So it should give you something like approximately $616.8 billion. That's the answer for part B. Okay, now, number 5. Hey guys, I got this example. It was during COVID because I believe it happened in the spring of 2000, and we were covering exponential functions. And right before we went to spring break, right after spring break, we went into lockdown. The classes resumed online. So the students and I, we came up with a scenario because we got the info from the news, right? I got the info from the news, and I was trying to show the students how exponential functions are related to the real world. So this was a good example to say for the students that math is everywhere. Okay, here's a problem. It states a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to about 128. Because I got this info because I believe it started in Washington State. There were 2 cases towards the end of January, if I'm not mistaken. And then by the end of April, the cases had grown to 128 throughout the U.S. So with this given data, we could come up with an exponential function, and then we could estimate how many people will be infected at any given month. Okay? So here we go. Here's how we start. For a part, they want us to find the model and that form f of t equals to y naught b to the power of t, with t equals 0 corresponding to the end of January, to the end of the month of January. So, right, so y naught is the amount present at time equals 0, which will give us 2. Right, so y naught is 2. So I already found my y naught. Now I need to find my b. Once I find b, I found the model that we're looking for. So then if t equals 0 corresponds to the end of January, then t equals 1 will correspond to the end of February. T of 2 corresponds to the end of March. And t equals 3 corresponds to the end of April. Right? So at the end of April is what we have here. There were 128 cases. So we can go straight from, right, this is my first point, 0, 2. This is my second point, 3, 128. Again, we're looking for B now. Right? So hey guys, here guys, right, when t is 3, y is 128. So we're going to plug him in here to the formula, right? So this will give us 128. The y naught is going to be 2. We're looking for the B. And the t is going to be 3. Right? Then we divide both sides by 2. It's going to give us 64 equals b to the third power. Now here, guys, we're solving for b, right? So we're trying to get rid of the 3 as the exponent. We want it to be like a 1. So we're going to raise it, both sides, to the power of 1/3. Why 1/3? Because b to the third power raised to the 1/3 power, you multiply that. When you go to a power, you multiply the power. So 3 times 1/3 will give you 1. And 64 to the 1/3 power will give you 4. So I found my b. So my y naught is 2, and my b is 4. So I got the answer for part A. F of t equals to y naught is going to be 2, my b is 4. So I found my exponential equation. Now, the second part, if the trend continues, about how many people will be infected by the end of the year? Okay. By the end of the year, it means by the end of December. So we count from the end of January to the end of December is going to give us 11 months. So we're going to evaluate the function on part A at 11, which means we're going to plug 11 where the t is. That's going to give us 8,388,608 people would be infected by the end of the year. Was this the case? Not that many people were infected by the end of the year because we used intervention. For example, we used social distance. I believe we also went into lockdown for a week or two, and also we had hand sanitizers. We had a lot of stuff to do intervention. But if nature would have taken its course, we could have estimated about this amount of people would have been infected. Okay, that's how we use exponential functions in real life. Now comes solving exponential equations. Okay, and here's my property. Since let A be a positive real number, with A cannot equal to 1. So here it is. If A to the U equals A to the V, in other words, if you have the same base, we let the exponents equal to each other. Okay, example. We have 3 to the x equals 3 to the 5th power. If you notice, we have the same base, right? So that means we can apply the rule, which means x must equal to 5. So the answer is 5. Okay, but not every time the bases will be the same. So at times, you're going to see if you can make the bases equal to each other. In this case, we can, because 125 is equivalent to 5 to the 3rd power. So I'm going to substitute 5 to the 3rd power for the 125. Okay. Now here, guys, we're going to apply the exponent power rule, which means when you have a power, a base to a power raised to another power, you multiply the powers. Okay. Now we got the same base, so we can apply the rule. We let the exponents equal to each other. So 3x equals to 5. Divide both sides by 3. So x equals to 5 over 3. And you can always check your work if you want. Okay, example. And we plug in 5 over 3 for the x, right? When we put in the calculator, guys, it's going to give us 3,125 equals to 3,125. So we know this is true. Okay, let me go back. That's how you can check it in the calculator, right? So I know this is a correct answer. Here's another one. Okay, right? The objective here, guys, is we always try to say, right, is 32 has a base of 4. Okay, so let's find out. 4, why not the same base? 4 to the first 4 squared, it will give us 16, not 32, right? So let's do 4 cubed. 4 cubed will give us 64, not 32, right? So now we know that we would know what that means, that 4 and 32 do not share the base 4 as a common base. So let's downgrade to something smaller. Okay, let's find the common base between 4 and 2. We know that 4 is equal to 2 squared. And 32 will be 2 to the 5th power. So now, right, we're going to substitute 2 squared for the 4 is. We're going to substitute 2 to the 5th power for the 32. Now on the left side, we apply the power property, the exponent power rule, which means, again, when you have a base with a power raised to another power, you multiply the powers. Now we get the same base, right? So now we set the exponents equal to each other. We distribute. It's going to give us 2x minus 2 equals 5. Now we add 2 to both sides. So 2x equals 7. We divide by 2. So x equals to 7 over 2. Again, we can check our work. Right, we're going to plug in 7 over 2 where the x is. So 7 over 2 minus 1 will give us 5 over 2. If you plug in 4 to the 4 to the power of 5 over 2, it's going to give us 32, which means 7 over 2 is the correct answer. Now here, guys, we're going to be writing exponential equations into logarithmic equations and vice versa. So here, guys, we have to know, right, that y equals to log of base ax means a to the y equals x. This, on the left side, is called the logarithmic form. On the right side, it's equivalent, right, to the exponential form. So these two are the same, right? Logarithmic converted to exponential, and exponential converted to logarithmic. Here's my conversion. So number 8, okay? It says, write each logarithmic equation into an exponential equation. So let's get the rule here. So we have to know what the a is, what the x is, and what the y is. We know that my a is equal to 9. My x is equal to 81. My y is equal to 2. Right? So it's going to be a is 9. So 9 squared equals 81. This is my solution here, guys. There's my a, there's my y, and there's my x. Now we're going to go the other way. We're going to go from exponential to logarithmic form. Again, right? So my a, we have to know what the a, the x, and the y are. So my a is equal to 5. My y is 3. And my x is 125. Now we go back to the logarithmic form. We're going to plug in the 3 for y, the 5 for the base a, and 125 for the x. And there's my solution. Right? Or you can turn that around. These two are the same thing. Okay? So again, you have to know the conversion from log to exponential and exponential to log. That's what's most important for these type of problems. Now graphs, right? Logarithmic graphs. So to graph logarithmic functions or graphs, you have to convert it to exponential. Example, if you have graph y equals to log of base 2x, okay, we have to convert it to exponential, where you give us 2 to the y equals x. So this is a function that I'm going to be graphing, right? So here, instead of plugging in the values for x, we're going to plug them in for y. Why? Because it's easier to plug them in for y, right? And then to solve for x. So here we go. Right? We have x equals to 2 to the y power. So when y is -2, it's going to give us x equals to 1/4. Right? There it is. And then we repeat the process. So this is what we get from the left, from the table on the left, we get the table on the right. So x is 1/4, y is -2. X is 1/2, y is -1. X is 1, y is 0. X is 2, y is 1. X is 4, y is 2. And x is 8, y is 3. Right, so we repeat the process. Right? And finally, we plug in 3, and we're going to get 8. There's my graph. Hey guys, I graph the exponential, which is in blue, and the logarithmic, which is in red. Here, guys, these two are called inverse of each other. But I believe in 1324, we don't cover inverse functions. So that's why I don't really go over it. But for the pre-cal for the 1314, they do cover inverse functions. But anyway, guys, the one in blue is the exponential function, and the one in red is my logarithmic function. Okay. Now, this is going to be expand or condense logarithmic expressions. So these are the rules that we got to apply. If you have log of base a of x times y, right, we expand it by doing the log of a x plus log of a y. The quotient rule, you have log of base a of x divided by y, there's going to be subtraction. So log a of x minus log a of y. If you have a power, right, the power will go to the front. So you have log of base a x to the power of r. The exponent, the r goes to the front. And similar with the Ln functions, which are the natural logs. Example number 11. You have log, right? If there's no base, it means it's base 10. Log of base 10 of parentheses x 5x to the fourth power y cubed close parentheses. So here, guys, we have the power property and the product property, right? Because here we have multiplications, it's going to be addition. And also, we also have the power property because if we have powers, right, they're going to go to the front. Need to add 3 separate terms, right? So if you have three, you have a 5, an x, and a y, right? So it's going to be 3 logs. There's 1, there's 2, there's 3. Now, right, because there's three like variables and coefficients, we have a 5, an x, and a y, so we have 5, x, and a y. Now, the exponents, they go to the front by applying the power property. Right? The exponent goes to the front on the x, and the exponent of y also goes to the front. So this is my solution right here, guys. We went from a single to expanded. Again, same properties. Now, this is a single log. They want you to expand it, okay? So here we have all 3 properties are present. Right? We have the product, right? Because if it's multiplication, it's going to be addition. We have the exponent, we have the power property, and we have the division, right? So we're going to apply all the 3 rules. Okay, now, so first, we apply the product property on top, right? Then we're going to apply the exponent. No, this one here, right? We're gonna expand these 2 here, right? Because if it's the product, right, becomes addition. Now we're going to apply the power property. The exponents, right, must go to the front. Right, the 2 goes to the front. Okay, now, how can you know if this is correct? Right, here on the left side, it's called condensed. Here on the right side, it's called expanded. So in the expanded form, you see, you don't have no exponents. You see, and the exponents really went to the front. That's why here for the exponent for the y squared, the exponent goes to the front by applying the third property, which is a power property. Here's you can check, guys, if everything on the left, right, on the right side of the property of the single to expanded is gonna match what's here. So this is my solution. Okay. Again, let's do another one. There are the rules. So now they want you to put it as a single log. So you're going to go from expanded to single, and this is a natural log here on the right. So if you notice, guys, the expanded form, right, as a single, for single there's no exponents, right? I mean there's no numbers in front, which means that here we have the power property and we have the quotient property. Right, so we have to execute the property, right? The coefficient that's in front becomes your exponent. Now we're going to apply the quotient property, right? If it's subtraction, it's going to be division under 1 natural log. This is my answer, guys, right there. Again, let's do another one. Hey guys, remember guys, when we're trying to solve with the same base, there's a way to get the answer right by using the properties. We're going to be using the natural log. So here, guys, right, to solve for x, we're going to take the ln of both sides, the natural log. You see, by rule, guys, by rule number 3 here, by the power property, the exponent goes to the front by applying that property. Now we divide both sides by the ln of 6. Use your calculator. There's my result. 2.386852807. Hey guys, make sure that you know, right, run it out to 4 places, that the ln, guys, is actually a number. The ln of whatever number it is, it's a value. You cannot separate the word or the letters ln with a number. They go together. It's an actual value. And there's another mistake that a lot of students make, because they don't know that the significant that the ln of something, of a number, is actually a value. Okay. Now we're solving. Here we're going to be using another rule. It says, this rule says, let u, v, and a be positive real numbers with a cannot equal to 1. If you have log of base a, u equals to log of base a, v, right? If the logs and with the base are the same, then the u must equal to v. If you notice, they both have to be as a single log. So in this case, the left side is okay, it's a single log, but the right side is not a single log. So we have to apply the quotient rule. Right? So with the quotient rule, right, we're going to write it as a single log, so it's going to be division. So it'll be log of x plus 3 divided by x minus 1. Now, right now, the bases are the same, right, because there's no base, means it's base 10. So they both are the same on the left side and the right side. Log of base 10x and log of base 10 of x plus 3 divided by x minus 1. So by applying the rule, we let the x equal to the x plus 3 over x minus 1. Right? That's where we apply the rule. Here you can multiply both sides by x minus 1 or just cross multiply. If you do that, we should get the same result. Now here on the left side, we're going to distribute. So give us x squared minus x. Now, since we have a quadratic, right, a squared, we're going to let the function be equal to 0, or the equation equal to 0. So we're going to subtract minus x minus 3 to both sides. to let it equal to 0. So we have x squared minus 2x minus 3 equals 0. Now we're going to factor. This will give us parentheses x minus 3, close parentheses, open parentheses, x plus 1, close parentheses, right? So these are the factors. So we're gonna get x minus 3 equals 0, or x plus 1 equals 0. So x equals to 3, and x equals to negative 1. Again, we can always check our work. Okay, just go on the next slide and check our work. Guys, if we use negative 1, right? If we plug in negative 1 for the x, it's going to give us error or not defined. That means the logs has to be more than 0. They cannot be negative nor 0. They have to be more than 0. So negative 1 is not a solution. Now let's plug in 3. Right, so here on the left side we have log of 3 with log base 10 of 3. So here, guys, right, if we put a 3, it's going to give us log of 6 minus log of 2. Here, right, we can use a calculator, or we can do it by applying the rules, right? If it's subtraction, right, if it's subtraction, it's going to be division with a single log. So log of 3 equals to log of 3, right? So we know the answer is 3. That's your answer. Solution. Now here's another rule that you have to be aware of. It says here, if you have a base, right, base A raised to the power of log of the same base of u will equal to u. So in this case, we're going to apply this property to solve for x. Right? We want to get rid of the log of base 4. We'll cancel it. How do we do it? Right? We're going to let this expression on both sides be my exponent. In other words, we're going to put a big 4, and this becomes your exponent, but we do it to both sides. Now, by applying the rule on the left side, right, this is equal to 1, so we bring down the 5x plus 6 equals to 4 squared, which is equal to 16. Then we subtract 6 to both sides. 5x equals to 10. We divide both sides by 5. X equals 2. And again, you can always check the solution. Right, so if we plug in 2 for the x's, it's going to give us log of base 4 of 16. Right? Here, you can put in the calculator, guys, right? As a change of base, you're going to put log of 16 divided by log of 4. And it should give you 2. On the left side, we apply the change of base. So the answer is 2. Okay, now comes chapter 5. We're done with chapter 4. For chapter 5, I only have 4 problems. Each one uses a different formula. So for the first one, it's called simple interest. It says, Gabriel invested his summer earnings of $3,000 in a savings account for college. The account pays 1.5% simple interest. What will be the value of this account after 2 years? And how much interest did he earn? So again, this is my formula. The future value of V equals to present value 1 plus R times T. So we're looking for the future value, right? Because it's in 2 years. So the present value is equal to 3,000. The interest rate will be 1.5%. Converted to a decimal will give us 0.015. My T is going to be 2 years, 2. So we plug into the formula. And we use a calculator. My answer is 3,090. Now for the second part, how much interest did he earn? The interest is equal to the future value minus the present value. So 3,090 minus 3,000. The interest is $90. So this is the answer for part A, 3,090. This is the answer for the second part, $90. Okay. Again, this is called simple interest problem. Now, let's do a compound interest problem. This is a formula for compound interest, but it's easier to use the second formula, the FV equals to PV, 1 plus I to the N. If you notice, guys, the I equals to R over M, and the N equals to MT. And here it tells you what everything is. The FV stands for the future value or future or majority value. The PV stands for the principal or the present value. The R stands for the interest rate per period. You have to convert decimal, right? Decimal from the percent. The M is number of compounded periods per year. The time has to be in years. The I, right, is the interest rate per period, which is the R divided by M. And the N is M times T, which is the total number of compounded periods. And here are the key words to use for M. If the problem states yearly or annually, my M is equal to 1. If it states bi-yearly or semi-annually, my M is equal to 2. Quarterly, my M is 4. Monthly, my M is 12. Weekly, 52. Daily, will be 360 or 365. Hey guys, it's only 360 when the book states to use 360. If the book doesn't state, it says just daily, then you use 365. And then continuous is a different formula. Okay. And these type of problems, compound interest can be used to invest a certain amount of money without depositing additional money. Here's an example. Number 18. You deposit $9,000 in an account at your bank that pays 2.5% interest semi-annually. How much money will be in your account after 10 years? And how much interest did you earn? So there's my problem, right? There's my formula. These will be easier to put in the calculator. So here, guys, what are we looking for? Most of the times, the last sentence or the last two sentences will tell you exactly what we're looking for. In this case, it's the last two sentences. How much money will be in your account after 10 years? So we're looking for the future value. So the present value will be the 9,000. The interest rate will be 2.5%. Will give you 0.025. My M compounded, let's see. Compounded, it says here semi-annually. So the M is going to be 2. My T will be 10 for 10 years. My I will be the R, 0.05 divided by 2, which will give us 0.0125. My N is M times T, which will give us 20. So plug everything in the calculator, right? So the answer will be $11,538.34. This will be in the account after 10 years. How much interest did you earn? So the interest earned will be the future value minus present value. So the future value was $11,538.34 minus the initial investment, which was the $9,000. That gives us $2,538.34 is the answer for the second part. Okay. Now, number 19 is going to be the future value of an ordinary annuity, which results in also a different formula, right? But it's easier. Right, so here, it says, at the end of each quarter, a 50-year-old woman puts $1,200 in a retirement account that pays 7.2% compounded quarterly. When she reaches 60, what will be the value in the account? And how much interest will she earn? So here, guys, right, we're looking for the future value, and the payment was $1,200. Interest rate 7.2%, which will give us 0.072. Compounded quarterly, so my N will be 4 because it's quarterly. My T, guys, here's where a lot of students get confused. Just because there's a 50 and a 60 there, they assume that for every number they have to put into the formula, which is not correct. Okay? If you read the problem correctly, it says that the woman put this money in the account when she was 50 years old. And when she was 60, she wants to see how much money is in the account. So from 50 years to 60 years, the time will be T. 10 years will be the time. So T is 10. Now the I will be R 0.072 divided by 4, which will give us 0.018. And the N will be M times T, which will be the 4 times 10 will give us 40. So plug it into the formula, right? So here I'm going to show you guys how to use the calculator, guys, in one steady flow without stopping. So first, you're going to enter the parentheses 1 plus 0.018 close parentheses to the power of 40 minus 1. This is what you should see in the calculator. 1.041320138. Then you're going to hit the division key, right? The division key because it's going to be divided by. Then this is what you see in the calculator, answer to the division, right? That means that this answer, the 1.04 divided by, now we're going to enter the 0.018. After you do that, you should see something like 57.85111.879 on your screen. All right? Now we're going to hit the times key, the multiplication key. This is what you should see on your screen. And then you're going to enter the 1200. So the answer will be 69,421.34245. Round it up to your nearest penny will give us $69,421.34. This is the answer for the first part. When she reaches 60, what will be the value of the account will be $69,421.34. Now, for the second part, how much interest will she earn? Okay, here, guys, right? We have to get the payments. How many payments did she make? She made 40 payments. 40 payments of 1,200. So how much money came out of her pocket? Or how much money did she invest it? So it's going to be 40 times 1,200, which will give us $48,000. That's how much money came from her pocket. So then, to find how much interest did she earn, we subtract the 48,000 from the $69,421.34, which will give us $21,421.34. This is how much money she earned in interest. Okay. Now comes the last one. The present value of an ordinary annuity. This one here is about buying a house or buying a car. In this case, we're going to be buying a house. It states, you want to purchase a $325,000 house with a 30-year fixed rate at 3.9%. What are your monthly payments and how much interest did you end up paying? This is similar to number 19, but instead of making money and interest right now, you're going to be paying money and interest for number 20. So again, this is a different formula. So here, guys, we're looking for the monthly payments, which means the money, the present value that you borrowed from the bank will be $325,000. Interest rate will be 0.039, 3.9%, 3.039. My monthly payment, so for houses, most of the time, guys, the M will be 12 because you have monthly payments. The 10 will be a 30-year fixed loan, so it's going to be 30. My I will be the R divided by 12, which will be 0.039 divided by 12. It results in 0.00325. The N will be the M times T, that 12 times 30 will give us 360. Let's plug everything to the formula. Now let me show you how to plug it into the calculator in a steady flow. So you're going to enter here the numerator, which will be 1 minus parentheses 1 plus 0.00325 close parentheses to the power of negative 360. So this is what you should see on your screen after you execute that. It's going to give us 0.68904,36901 on the screen. Now we're going to hit the division key. Once you do that, you're going to enter 0.0035325. And this is what you see on your screen. You're going to see 212.0134431 on the screen. Now you're going to press the inverse key. Right? Every time that you have money on the right with a payment and money on the left, we're going to use the inverse key. It's much, much, much more easier. Once you get the inverse key right, this is what you should see on your screen. Then you're going to enter the 325,000, and this is your monthly payment. So your monthly payment is going to be $1,532.92. Now, that's the answer for the first part. For the second part, how much money did an interest did you end up paying? So again, similar to number 19, it's kind of similar. You made 360 payments, and each payment was $1,532.92. So you're going to multiply the payment times the number of payment, and the payment times the number of payment, which will give us $551,851.20. That's how much you end up paying for the house. So how much did you end up paying in interest? So we subtract the money that you borrowed, right, the $325,000 from the $551,851. So you end up paying like $226,851.20 in interest. That's a lot of money. The only way you can pay this interest is if you give like an extra to the principal every month, or every time that you have extra money, just put it to the principal. This way, it'll begin to eat the interest. That way, you don't pay that much interest. Okay. I believe this is it for this PowerPoint. If you have any questions, let me take it back to the host. If you have any questions, please let me know so I can help you, or we can help you, myself or the tutors. Thank you, Rich.
Thank you, Mr. Sassi, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist, and this session will also be available on that playlist later today. Also linked was a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey before you all leave. And before you all leave, I want to share the TVE sessions that we will have next. At 1 p.m. today, we will have a presentation from the Writing Center and Succeed with CSD, and we'll be back with Happy Math Hour next week at 11 a.m., where Math 1314 will cover exponential and logarithmic functions, and Math 1324 will cover systems of equations. Our 1 p.m. session next week will be the presentation Libraries with Blake Klimasara. Thank you all for coming in today. We hope you all have a lovely weekend. Thank you again, Mr. Sassi. And as he said, if anybody has any questions, feel free to use the chat box or your mic. And we hope to see everyone again for Happy Math Hour.